Assalamu alaikum. Bismillahir Rahmanir Rahim. I welcome you to the 42nd lecture for the series of lectures on advanced computer architecture. Today we will continue our discussion onto the networks and clusters. After a brief review of what we discussed last time, today I will be talking in details about the distributed switch topologies, internetworking, and clusters. Last time we discussed the formation of generic interconnection networks and their categories. Here we said that the network's communication model, its performance, media, the role of software, protocols, subnets, and network topologies. We noticed that a generic interconnection network comprises, number one, computer nodes, which are also referred to as the host or end systems. Then it comprises the hardware-software interface and links to the interconnection networks and communication subnets. The interconnections are classified based on the number of processors, which are also known as the nodes, and the distance between the nodes. Based on these two criterion, the networks are classified as the local area networks, wide area networks, and system area networks. These are abbreviated as the LAN, WAN, and SANs. Then we talked about the interconnect communication model. Here we said that the communication model shows that two machines are connected via two unidirectional wires with a first in, first out buffer, which is also known as a queue, and this queue is used at the end to hold the data. Furthermore, we noticed that the communication software separates the header and trailers from the message, and it identifies the message being a request, a reply, or their acknowledgements, and error checking codes are also included into it. The communication protocols suggest that what is the sequence of steps which is to be taken for reliable communication. The network performance that defines the latency of the message as the sum of number of parameters. These parameters are the sender overhead, time to flight, receiver overhead, and the ratio of the message size to the bandwidth. Last time we also discussed the properties and performance of interconnect network media, or say the links. Here we notice that the media used are either the unscheduled twisted pair, abbreviated as UTP, or coaxial cable, or the fiber optic. Last time, at the end of our discussion, we studied the formation of bus-based and switch-based communication subnets, and we introduced different network topologies. Here, while talking about the network topologies, we observed that the bus-based LANs or Ethernet is the simplest way to interconnect more than two computers, where these computers share a single media, which means there is only one wire, and this wire is used as a single media to interconnect more than one computers. However, here we notice that the interconnects sharing single media is a challenging option, as it requires coordination and arbitration when more than one computer needs the same media simultaneously. However, we notice that the alternative to sharing media is to use a switch, where this switch is used to provide a dedicated line to all the destinations in a particular sequence, and it facilitates the point-to-point communication much faster than the shared media or the bus. Here we notice that a switch provides unidirectional interconnection of inputs to any one of multiple output terminals. Furthermore, the switch that facilitates unidirectional interconnection of every processor to all the processors in the network is referred to as the non-blocking switch. The example of a non-blocking switch is a crossbar switch, where this crossbar switch is employed in the central switching topology. Last time, we also discussed the crossbar topology in detail and noticed that a crossbar uses n scarce switches to interconnect n processors in a network. Here, the routing to establish interconnection between two nodes at a time depends upon the addressing style. That is, the two different styles are used, namely the source-based and destination-based. The source-based routing is one where the message specifies the path to the destination, which means that the destination address and the complete route is contained within the message. Whereas the destination-based routing is one where the message simply contains the destination address. This means that it does not contain the complete route from the source to the destination. Rather, it uses a program which is running in the switch to select the port to take a desired route for the given destination address with the message. However, today, continuing our discussion on the centralized switching topologies, we will discuss an intermediate class of network interconnects. Intermediate class means a class of interconnects which lies in between the crossbar topology and the bus-based network topology. This intermediate interconnect topology is usually known as the multi-stage network topology. Centralized multi-stage switch is shown here. Here you can see that this switch is built from a number of large switch boxes, and these switch boxes are placed at number of stages to interconnect all the nodes. Here in this figure, you can see that the crossbar switches contained at each stage are usually 2x2 switch, and it allows a straight connection and a cross connection, where the straight connection is just end-to-end connection in the same line, whereas the cross connection is connection in a cross manner. The number of stages in this type of arrangement are related to the number of nodes and the size of the crossbar switch. Consequently, its performance as well as the cost both are more scalable than the bus-based network, because it depends upon the number of stages and the size of the switch, and ultimately it makes both the cost as well as the performance being scalable. The number of identical stages, denoted as NS, in the network having n nodes and switches of size m by m in each stage, can be calculated as it is equal to log of n to the base m, which means the log of the total number of nodes to the base of the size of the crossbar switch. And the number of switches per stage can be calculated as it is equal to the ratio n by m. Thus, the total number of switches used in the multi-stage network of n nodes is n divided by m multiplied by log of n to the base m. That is, we can say that its cost is of order n multiplied by log of n, and this cost is much smaller as compared to the cost of a crossbar switch, which is of order n square. Now, in order to understand the design and working of multi-stage networks, let us consider a topology known as the omega network topology. And this omega network topology is shown here in this figure, where it is a typical application that contains 8 nodes, or say 8 processors, and the addressed using 3-bit code and 3 stages of 2x2 crossbar switches. Here, if we use the previously defined formula, then we can find out the number of identical stages as equal to log of 8 to the base 2, which is equal to 3, and the switches per stage, which is equal to n over m, or it is equal to 8 divided by 2, resulting in the total number of switches at each stage to be equal to 4. And it is shown here in this diagram that the 4 switches are placed in a column, in a 3-column structure over here, and the 3 columns show the 3 stages of the multi-stage switch. Here, let us see how the switches at each stage operate to establish the connection between two nodes. Notice that for the 8 nodes omega network, the node address is of 3 bits. Because there are 8 nodes, definitely the address will be ranging from 000 up to 111. And this is also, that is, the number of bits is equal to the number of stages in the switch. Here, the 3-bit code, for example, we can say A2, A1, A0 may be used to represent the 3 stages of the network, that is, the stage S2, S1, and S0 respectively. And these stages on this diagram are shown marked from left to right. That is, the leftmost stage is S2 and the rightmost stage is S0. Here, to find the connection pattern, exclusive OR operation is performed onto the source address and the destination address. For example, if we want to establish a connection from the source address 010 with the destination address 110, then exclusive OR operation onto these 2 coded values result in a value which is equal to 100, and it shows that the leftmost stage is equal to 1, which shows that its connection is a cross connection, whereas the other 2 bits show the second and the third stage, that is the stage 1 and stage 0, and these 2 stages have the straight line connection. The switch connection over here are shown by green colored circles. Here you can see that the generalized rule to find the switch connection can be summarized as, we can say that for any stage I, if the source and the destination differ at ith bit, then the connection is cross, because the exclusive OR operation on 2 complement values is always equal to 1, and whenever its value is equal to 1, the connection is cross. Otherwise, the connection is straight in that particular stage. And this is clearly shown in our example which we have already depicted. However, there exists a single path from the source to the destination. Thus, contrary to the non-blocking crossbar network, we can say that the omega network is basically a blocking network. Now, this is shown here in this diagram by marking the red path, that where exists the blocking. Here you can see that the path from the source address 010 to the destination address 110, here it is marked in red color, and the path from 110 to 100 is shown in the blue color. These 2 have the blockage as the S2 for 110 has to wait till 010 has passed, otherwise the result will have a collision. However, in order to minimize the collision and to improve the fault tolerance in the omega network, which is essential to achieve high reliability and dependability, we have to introduce some extra pathways, which means that some additional paths are to be generated for different interconnections to work simultaneously and to avoid the collision. This can be accomplished by making use of another topology known as the butterfly topology. The butterfly topology shown here is an alternative arrangement where irrespective of the source address for a given destination, the ith switch sends a value either to the upper port or to the lower port, depending upon the value of the ith bit. That is, if the ith bit is equal to 0, then the connection is established with the upper port, and if the ith bit is equal to 1, the connection is established with the lower port. So this type of arrangement, in fact, to some extent, overcome the blocking problem, but it is not a guarantee. However, this butterfly switch or the omega topology is interchangeably used depending upon the requirement or the level of reliability and dependability. Now, with this much discussion about the centralized distributed multi-stage arrangement, let us talk about the distributed switch networks. The distributed switch network is one where the switches are distributed throughout the network. That is, they are not placed at a centralized position. Rather, the switches are distributed throughout the network, and they allow interconnection of one node to another, either by facilitating the connection to all the nodes, or it may be to a limited number of nodes. So the distributed switching network has got some different types of limitations and bottleneck as compared to the centralized switch network. A distributed switch network where each node interconnects all the nodes of the network is known as the fully connected network, and it is shown over here, a 4-node network where the node A is connected to B, C, and D, node B is connected to A, C, and D, and so on. So here you can note that there exist interconnects for distributed networks. However, before we discuss these interconnects in detail, let us understand the parameters of the interconnect performance measurement, because we have to see which type of network is having a better performance as compared to the other type of the network interconnect. The most important criteria for the measurement of the performance of distributed topology include, number one, latency, where latency is the measure of the number of links, and for any network to have a good performance, the latency must be small, which means that the number of links for a message to pass from the source to the destination must be kept small. The second important criterion is the bandwidth. Bandwidth is the number of messages or the length of message that passes a particular switch and that can be used for communication from one point to the other point, and the performance of a network is good if its bandwidth is large. The other third parameter is the node degree. The node degree, or the degree of the node, is in fact the number of links connected to a node. That is, to a particular node, how many links are being connected. For example, in our previous fully connected network, 3 links are present at each node. Therefore, we can say that its node degree is equal to 3. Another important parameter is the measure of the diameter. Diameter is the maximum distance between any two processors, and the distance is in fact measured in terms of the number of nodes between the source and the destination. This is indeed the measure of the latency of the network also, and it is actually the maximum latency which is associated with a particular network. The other important parameters are the bisect bandwidth. The bisect bandwidth is in fact an imaginary line that divides the interconnect into roughly 2 equal parts. That is, if this is a complex network having different nodes at different points, and there are some interconnects, we can draw an imaginary line crossing the whole network such that the network is divided into roughly 2 equal parts, and each part has got approximately half the number of nodes. The important result from this is in terms of the bisection bandwidth. The bisection bandwidth is the sum of the bandwidth of the line crossing the imaginary bisection lines. So the number of lines, if I have placed a bisection line over here, how many lines are crossing when we move it we have to see, to establish a link, how many lines are crossing from here. It, in fact, measures the volume of communication which is allowed between any two halves of the network. For example, if there are a number of lines crossing this imaginary line, so in fact, it is the measure of the total volume of the communication which is allowed between two sections of the network or two parts of the network. So, with the help of these parameters, we can determine the performance. Here, you must note that the bisect is, in fact, cannot be clearly measured if the network is not symmetric, which means for the non-symmetric networks, the measure of the bisect is not clear. So, this means that in order to draw the bisect line, the bisection bandwidth is usually considered. However, it is to be noted that the bisection bandwidth is indeed the worst case metric of non-symmetric interconnects. Therefore, the division of the bisect line that makes the bandwidth worst is to be chosen. Now, with this much discussion, let us have a look into different types of distributed switch topology. The most popular types of topologies are the linear array or ring topology, the fully connected topology. The two-dimensional mesh are torus, hypercube, and trees. Let us have a look into these architectures and see their performance. Let us first of all consider the simplest possible low-cost distributed switch topology, which is the linear array or the interconnection slightly modified to convert it to ring network. A linear array is shown here in this diagram, where you can see that actually a small switch is placed with each processor or say at each node, and this switch in fact facilitates the connection between the nearest node and the current node. For example, for a linear array, the switch at the ith node connects this ith node to the node on the left and to the node on the right, which means that it facilitates or it can connect to I minus 1th node except for I is equal to 1, that is at the leftmost end of the array. And similarly, it can connect to the I plus 1th node except for I is equal to n, that is the rightmost node. So in the linear array, as the ith node is connected to I minus 1 and I plus 1th node, therefore the message will have to hop along the intermediate nodes when it is not the just next node. That is, if it is not, the destination is not the I plus 1, rather if say presently the source is at the any position I and the destination is at I plus 4, then it has to hop through and finally it reaches the destination. Linear array can be converted to a ring network by establishing an interconnect between the first node and the nth node in the array as shown over here, which means that the nodes at two ends of the array, if they are interconnected, then this type of network is known as a ring network. Here, a ring network has some message hopping along the intermediate nodes until they reach the destination. However, it allows many transfers simultaneously. For example, the first node can send to the second node at the same time when the third node can send to the fourth node, and so on. However, a variation called token ring is usually used in the ring network, and this technique simplifies the arbitration in the ring topology. Here, a single slot known as a token, it goes around the ring to determine which node is allowed to send the message. So basically, it is a token which is moved from one node to the other node. It contains the information that which node is to send the information. A node can send a message if it gets a token. The common performance of an n-node linear array and a ring network is such that a linear array or a ring network is cheap in cost because its cost is of order n. The overall bandwidth of the network is high, and the latency is also high as it is of order n. However, there is a small variation in the performance of the linear array and the ring networks. There are some common features and there are some different or varying performance parameters. For example, the degree of both the linear array as well as the ring is same. It is equal to 2, whereas the diameter of the linear array is n, whereas that of a ring is n by 2. The bisection width of the linear array is small. It is equal to 1, whereas that of the ring is equal to 2. The bandwidth of the linear array is n minus 1, and that of the ring is equal to n. The mean latency of both these arrangements is the same, which is equal to n by 2. The major difference is that a linear array can be regarded as an asymmetric network, whereas the ring is a symmetric network. So with this much introduction about the linear array and the ring networks, now let us talk about the fully connected topology. It is a straightforward, symmetric, but expensive distributed network which is equivalent to the centralized crossbar network. Here, every node has a direct link with all the other nodes of the network. We have already introduced this in the beginning. However, its performance metrics are that its diameter is equal to 1, which means that there is only one link between every two nodes. Therefore, whenever it has to establish a communication, the diameter is equal to 1, but the degree is equal to n minus 1, and the number of links is equal to the product n and n minus 1 divided by 2. Bisects equal to n square divided by 5, and the bisection bandwidth is proportional to n by 2 whole square. Now let us consider two-dimensional mesh or two-dimensional grid and two-dimensional torus distributed switch network topology. The two-dimensional mesh or grid is in fact an example of asymmetric network topology, and it uses the bisection bandwidth as the performance metric. The structure of a 2D mesh is shown over here. Here you can see that the nodes or the processors are arranged in an two-dimensional array structure. For example, the shown structure is a 3 by 4 mesh. Here, as you can see, that a switch is associated to each processor or each node. Here it is shown with the help of a blue dot. Each switch has one port for the processor and 4 ports to interconnect the processor to the 4 nearest neighbor nodes. That is, the node to the left, right, and up-down position from any ith node. However, this structure is sometimes also referred to as news communication pattern, where the word news represent the north, east, west, and south. So basically, this shows that the ith node allows four-way communication. Here, note that the switches are associated with the top and bottom rows as well as the left and right columns such that there does not exist any connection amongst themselves, which means that the leftmost switch in the first row is not connected to the rightmost node in the same row. Similarly, the topmost switch in any column is not connected to the bottommost switch in the same column. However, if any design is slightly modified by connecting these unused ports of switches of the top and bottom rows or the left and right columns, then this 2D grid is converted to a new structure which is known as the 2D torus. Now, this 2D torus is shown over here, where you can see that the routing can be established by moving first in the horizontal direction and then in the vertical direction. Either horizontal is either from left to right or right to left, and the vertical is from top towards the bottom or from bottom towards the top, depending upon the source address and the destination address. The performance metrics of n-node 2D mesh or n-node 2D torus are that its degree is equal to 4, diameter is equal to 2 times square root of n, the number of nodes, bisect width is equal to square root of n, the bandwidth is equal to n, and the structure is asymmetric structure. Now let us consider another example of distributed switch network. Another type of distributed switching network is the tree topology. Here, the switches associated with each node have the number of ports equal to the number of branches of the tree plus 1 for the processor. Here you can see a binary tree structure which has got 2 branches of the root node, and all branches have 2 sub-branches. The performance metric of n-node tree network are that its cost is of order n, so it is a cheap arrangement. Its degree depends upon the number of branches. That is, it may be equal to 1, it may be 2, 3, and so on. For example, for a binary tree, its degree is equal to 2. The latency is of order log of n to the base equal to the degree, and the diameter is twice the latency value, that is the 2 times log of n to the base degree, and its bisection width is equal to 1. However, in the tree network, the root node and the branch nodes of the leaf nodes are the basic bottlenecks. That is, they are in fact having some hurdles in the communication. For example, as shown in this diagram here, the leaf nodes 1, 2 of the branch node number 9 and the leaf nodes 3, 4 of branch node number 10. They may be interconnected simultaneously, but the leaf node 1, 3 and the leaf node 2, 4, they cannot be connected because the possibility of having a collision at the branch nodes number 13, number 9 and number 10 will become definite over here. However, in order to avoid this bottleneck in the tree, another tree structure is proposed or used, which is known as the fat tree network. Here, this fat tree network avoids the bottleneck of the roots by facilitating multiple paths and by providing these paths between any two nodes, as you can see it from this diagram. Now, in this structure, we show the processor memory nodes connected through the multiple stages of 2 by 2 crossbar. Second level is 4 and 2 plus 2 crossbar switch, and the next level is 8 is to 4 plus 4 crossbar switches, and so on. This basically arrangement is a three-dimensional switching arrangement, and it increases the bandwidth via extra links at each level over the simple tree. This type of structure has been used in the CM4 architecture of the multiprocessing system, and this fat tree concept is used as a centralized switching network. However, in these topologies which we are going to talk about today, the last topology is the hypercube network topology. This is another example of the distributed switch network. It is also known as the binary n cubes, as you can see it from this diagram that it has two nodes each of n cubes. It is basically an n-dimensional interconnect for 2 raised to power n nodes. As you can see it from this figure that for all the 16 nodes, the hypercube is a 4-dimensional structure, as you can see over here in this case, where n is equal to 16, it is equal to 2 raised to power 4. Therefore, it gives us a value of a small n equal to 4. Here you can see that it requires n ports per switch plus 1 for the processor. Then this have n nearest neighbor nodes. Thus, we can say that it minimizes hopping and it have latency of order log of n to the base 2. Here, the other performance metrics are that a hypercube has number of nodes equal to 2 raised to power n, where small n is the level of n cubes and capital N is the total number of nodes. The degree is equal to small n and the diameter is also equal to small n. Links are equal to small n multiplied by 2 raised to power small n minus 1, and bisection width is equal to 2 raised to power small n minus 1. However, the other topologies such as tree, mesh, etc., they can be embedded into the hypercubes. Note that the bisection bandwidth is good over here, but it is difficult to lay out in three-dimensional space. The hypercubes have been popular in early message passing machines. For example, the Intel IPSC, the N-cube, etc. The other extension of the hypercube is K-array N-cube network topology. Here, rather than having just two nodes of small n cubes in the binary hypercube, the generalization of hypercube is to interconnect k nodes of n cubes in a string. This gives us the total number of nodes to be equal to capital N, which is equal to k raised to power small n. For example, 64 node K-array N-cube network is shown over here. Here, the value 64 is equal to 4 raised to power 3, which gives us 4 array and 3 cubes. It is area over here, which is a 3-cube structure. And these similar 4 sets of 3 cubes are repeated in this structure. With this much discussion about the distributed switch network, we conclude our discussion for today, where we have completely discussed the intermediate class of network interconnects, which lie between the crossbar and bus-based networks. This stage is known as a multi-stage switch network topology. Then we talked in detail about the distributed switch topologies, which include the fully connected networks, 2D mesh and 2D torus. Then we talked about the tree topologies and fat tree and hypercube topologies. We conclude our discussion over here today, and next time, inshallah, we will discuss the internetworking and clusters. We will also discuss some practical applications of all the concepts which we have studied so far. So I say you Allah Hafiz till next time. Thank you.